Let's see. Next we have Arshad Hussain. Let's see. Arshad is a Linux kernel programmer. He joined Seagate's Lustre team at the end of 2015. He works on Lustre bugs and improvements. Arshad, let's give him a hand.
Thank you, Stephen. Hello, everyone. So today's topic is online patching for Lustre. And this is a work in progress. We got it going for 2.7, and we got it working for 2.7, and it's kind of a work in progress for now. So we move on to agenda. So we want to, I want to just say that we'll discuss Kpatch basics and how the Kpatch is applied, Kpatch limitation, Lustre issues which was found, Lustre changes completed. We'll discuss a little bit about Lustre test and open issues and future work. So Kpatch technology was introduced by Red Hat in 2014. So this is essentially a technology that you can patch the running kernel immediately. This is licensed for GPL v2. So what it does is, what Kpatch basically does is that it uses already a kernel feature which is there for tracing, called ftrace. And once you build with Kpatch, once you build with ftrace, what happens is that the compiler builds the no-op on top of it. It builds with the no-op, which essentially is used by ftrace to actually hook on to tracing. What Kpatch does is that it uses this to hijack and then return to a new function, essentially giving impression that the new function is running as if nothing has happened. So I'll discuss about stop machine in a while, but it has a single switching point. That means either the new patch is running or the old patch, the new patch module load is failed and the old patch keeps running. So it's pretty safe because of using of the stop machine. It is compatible with kdump and crash. That means the new function is agnostic to kdump and crash. You'll see everything similar to what it is. And Kpatch also have user hooks, which I'll discuss a little while. So first, Kpatch process. So as we can see that we have an original source, and from that source, original module is built. Now, this module, there is a requirement, so be it. So we changed the patch, we changed the source, and Kpatch provides two utilities called Kpatch build and Kpatch load. The first utility is Kpatch build, which essentially prepares the source in such a way that it could be inserted. In this slide, we move on from 1 to 2, where we have source, then from 2 to 3, where we have a new patch KO. And step 4, we see that we have already running module, and then we have a patch module. So Kpatch also have a second utility called Kpatch load, which allows the Kpatch to load and unload the module. So in this case, if we give Kpatch load followed by a new patch, this is where the stop machine comes in. It freezes all the threads and interrupts. It goes and checks all the stack and sees that if none of them is running, call stack basically, and if not, it jumps on the return address, it modifies to run the new patch. If it fails for some reason, your old patch keeps running, nothing is lost there. The good point about load is that you can have incremental loads and you can bring it down. So it's like a stack, it goes up and goes down. So the fifth step is that once the Kpatch load is actually completed, you see your new patch running. So the whole flow which is shown here, we'll actually see in respect with how we have done it for Lustre. So, but before that, we'll just go through a little bit of Kpass limitations. So the Kpatch it doesn't patch variables or structure, it replaces the whole function. That means if there's an attempt to change a single static variables, those kind, it could be done, but it's not recommended, and it's actually used to replace the whole function. So the second is the Kpatch, it cannot patch the running functions. What this implies is that if you have a patched module which you want to insert, and it touches a lot of function points, and one of them is actually running, and if you stop it using stop machine, and it could actually break the system or it could cause side effects, then of course it cannot run. So Kpatch makes sure that using stop machine, it stops all the threads and interrupts to freeze all processes and threads before making switch to a new function. And as I've said that it does not modify statically allocated variable. Any variable will have a scope of a lifetime. It is recommended not to do that. Kpatch is actually used to patch function in full. So the Lustre issue, what we found while applying the online patching or the Kpatch to Lustre is that our goal was to actually do a POC in such a way that we could demonstrate that there's no active process, there's an active process in queue, and we could apply it even though we are doing a testing and I/O which is going on. What Kpatch does is uses a diff. So if you look at a debug log, so it says that the line number which is highlighted in red, so it uses a macro __ line. This signifies that, and this macro changes for every line, resulting in the patched module to be very large. Once the patch module is relatively large, it takes long time to insert, which actually has a side effect, which I'll discuss in a little while. So the first thing was this. So even though we were changing one small line, because of this, we were generating and hitting a lot of entry points there. So the second is static variables and debug logs are removed. So this is kind of, we put it here, but so any static variables and debug logs, if any, would be removed here. So the delays during stop machine. So as step number 5 said, that when you're doing a Kpatch load, it stops all the threads and interrupts, switches to a new function. It does some safety check before switching. So if that safety check is expensive and time consuming. So what happens is if you have a module that touches a lot of entry points, the eviction tends to happen. So we circumvented that by having a user hook to actually reset the timer, but Kpatch essentially is, it's ideal for having hot fixes, which is minimal in size, and consumer vulnerabilities kind of a thing. And the final point in the issue found was to minimize the live objects. That means that we made sure that we had RPC barrier and no process was active when we were actually doing a Kpatch load. Lustre changes that was completed to get it working was, the first thing we did was to get less debug info. So we removed the line numbers and marked hard-coded as 0 for now. We'll see how to circumvent this in future, but for now, if this is a hot fix, we could still get away with it. We still have a git hash and we could still home on to a line number that way. But for a POC like this, we made sure that we were not, the underscore line underscore was not causing a lot of function to be touched, and we just removed the line number to be 0 for now. So no use of static variables in debug logs. And to make calls from thread main function to non-static function only. That means that, so any function is a function pointer, we make sure that we don't touch that. And so because that increases the calls, touches the call stack, and it increases the time for the Kpatch load to insert. And finally, we have added a PTL RPC barrier with timeouts. And the step taken was to stop processing of incoming requests, except BRW and cancel. So that we'll show it with an example, which is coming through next. So disable BRWs, disable cancel as a step 3, flush buffers and all commits. Stop barrier and abort patching on timeout. So once the step is done, we can see that in the results later that modules are inserted there. And the only thing is that we add a hook to refresh the timers. So the other way, what we've also experimenting is that we could actually change the timers up front and then start the PTL RPC barrier. So these are the test results to simulate 2,000 clients. Actually, these are 10 clients with IB network, 200 mounts per clients. And this is a simple command which has been executed, a simple DD command. And the server it has 2 MDS and 2 OSDs. So this is what we get when we do a Kpatch load here. So you can see that it spits out 3 important information here. In this case, all active requests, that means all active requests minus cancel and BRW requests, it's 0 for now. You can see that cancels and BRW request is 289, and all cancel requests is 0. So N requests active, this is what holds, this is the modification that has been done, which holds all the information about active, cancel BRW, and cancel request. And finally, the third last line says that it took 1 second for the barrier, and the Kpatch was a success. So this one was on the OST side. This test was on the OST side. This is a racer test on 10 clients with 50 mounts per client, and the command executed is racer. That means this is on the MDS side. The server configuration stays the same, which is MDS count is 2 or OST count is 2. So again, the same Kpatch load was applied, the same results here. It's just that all active requests minus cancel and BRW in this case was a little higher. Cancel and BRW was 0, and the cancel request was 0 in this case. Just so Kpatch gives that ability to actually immediately patch a running kernel. What we did was we did series of changes to make sure we could make it run it on Lustre. So we could also run it on a single node by making a little small modification on the client side too, where we added a freeze unfreeze, which was just returning 0 for now. But this is purely on the server side. Client, we are not concerned for now. And the results for now is that we could successfully do it for DD, we could successfully do it for Racer, for multiple clients and huge mount points. So this being a work in progress, so we still have open issues, and there's a future work on this going on. So the most primary is that we need to test across the gamut of all subsystems, all components beyond I/O, that is MDS, LOD, OSP, OSS, test across with the stress I/O using complex racer or sequential I/O, basically stress it out and then try loading patches which covers real life bug scenarios, those kind of a thing. That we have not done. That's still pending, which essentially boils down to test with complex setup with larger clients and OSS. And most importantly, what we have not done is we have not looked into how this will be addressed as a deployment process. That means once we have a patch module, how will that be signed? How will actually that goes to client? How will client install it? There are a lot of ideas saying that we probably should be having a repo, and once everything is tested, a client could simply yum install and just run it. But those kind of things, it's still work in progress, and we have not touched yet. It's a future work for us. So I've quickly completed it, so I'll take your questions now. Or like you can yell. Sorry.
I'm so sorry. We have a great question from almost the back row. No. Okay. All right.
I mean, I always have questions, but I don't want to be the only person asking questions here.
Sure.
Anyways, one question, does this hook in with the kernel freeze architecture so that you could potentially do like suspend and resume of Lustre clients or something like that? Because I know there's hooks in the kernel for, laptop suspend and resume, and they allow you to, flush state like RPCs in flight and things like that. If we were to hook into them, we've just never implemented it. I'm wondering if this is how you did your barriers and things.
And this, is your question asking how we have implemented barriers?
Yes.
Okay. And Andrew, you want to answer?
We implemented freeze and freeze hooks for clients, but the main intention was to use Kpatch on the server side, so we don't need it. But it works. We tested it with clients also. So.
Since you are mostly concentrating on the server side, did you compare this like 25 seconds with actual failover times? Like, is there actually a big win over there versus doing a real failover that is much faster nowadays than it used to be?
Correct. So what your question is that the timeout issue, right?
Your whole thing shows that you did your live patching in 25 seconds. So did you try the same scenario, but do a real server failover where you don't play any of those tricks, but just, do a failover? How long did that take? Like, how much time are you winning? Is
Correct.
This cat worth skinning?
True, Alex. So no. So we have hooks to actually modify timers, but we have not tested that. That part for the failover, it's a good question. We have not tested it. Still, we have to verify that part. Andrew, want to add something?
With failover, there is another issue when clients reconnect. It may extend this time for failover for a long period. In this case, when we apply in Kpatch, we have a fixed time for applying. We have not measured it on the real system.
Any more questions? Thank you very much. Just finally, I want to thank Andrew. He's the project lead for this and a great mentor. Now, thank you.